Engineer Man here. Time to learn about buffer overflows and stack and heap corruption. No time to waste. Let's do this. Today's level is intermediate. I'm assuming you know what a buffer is. It's the only assumption I'm making today. So first was buffer overflow and stack and heap corruption. Buffer overflow occurs when you allocate a set amount of memory but write more data to that memory area than it can hold, such as allocating 12 bytes but writing 16 to it. Once you've done so, you've now corrupted your stack or heap. Anything can happen after buffer overflow, including nothing, memory corruption without a crash, or memory corruption with a crash, to name a few. Now for an example. I wrote a small program here, and what we're going to do is we're going to take two buffers. So I have buffer 1 and buffer 2. I've initialized buffer 2 with the words overwrite me. And it's slightly less than 16 bytes, but that doesn't matter. Buffer 1 is uninitialized, which I'm setting down here as nothing, but we'll continue changing this over the course of the video just so you can see what effects it has. So let's run it once because I want to show you the memory alignment for these two variables. So we run it once. We can see that buffer 1 is located at 30 and buffer 2 is located at 40. Now this is hexadecimal, so this means that buffer 2 is located 16 bytes to the right of buffer 1. So that's good. So what we're going to do here is we're going to write some data to buffer 1. So we're going to write 15 bytes, well, 15 characters, and then string copy is going to put the null terminator on the end, so that's going to be 16 bytes. And then let's look at the effect. Everything works fine. Everything's perfect. We have 16 bytes here, including the null terminator, and then we have buffer 2, which has been unchanged. What if I add the 16th character, and then when it adds the null terminator, it's going to be 17 characters. We've now overflown the buffer by 1. Watch what happens. Oh no, buffer 2 is gone. Not good. But it's actually, it's not actually gone. What happened is it wrote the null terminator onto buffer 2. Because this is 16 characters, the null terminator would have been the 17th character. Because buffer 2 is 16 bytes to the right of buffer 1, it would follow that the very next character it writes to is the first byte on buffer 2. So now buffer 2 actually has a value of null terminator. And we can see that by just adding a couple more characters onto buffer 1. So now what we've done is we've overflown the buffer by 4 characters. Rerunning the program shows that now it's on buffer 1 as well as buffer 2. Buffer 2 is now 7, 8, 9 and the null terminator. Not good. So if we reverse these, now the reason you don't get a seg fault is because you only get a seg fault when you do a buffer overflow and you write into memory that you don't own. So in this case, technically the program owns the address space for buffer 1 and buffer 2. Therefore, while you've done something illegal here and you've done something that causes undefined behavior, you haven't technically touched anything that the operating system owns or another process owns. So let's actually change that. So what I'm going to do now is I'm going to, instead of copying data into buffer 1, I'm going to copy it into buffer 2. And then we're going to see what it takes to get a seg fault. So right now I've copied 21 bytes into buffer 2. And you can see that I got junk in buffer 1. That's fine. So let's just double this up. Now you can see I've seg faulted. And the reason I've seg faulted is because now I've overran buffer 1, buffer 2, and whatever memory is allocated for the program that you don't see, and then I've gone off and I've tried to corrupt memory for another process or for the operating system itself. Now the operating system's not going to allow that, therefore I get a seg fault. Now that was stack corruption. If we want to do heap corruption, it's the exact same thing. Whether you've malloc a string or you've used a fixed width buffer, it's exactly the same. The result's going to be the same. The only difference is you're going to be corrupting heap area rather than stack. Now one final point. When I compiled this program, I had to use no stack protector, which is a GCC option. Now, the stack protector, what it usually does is it'll see when you've overflown a buffer, and then it'll just terminate your program. Some versions of GCC have this enabled by default, other versions have it disabled by default, so you can't really count on it. However, you can use it if you'd like. There's pros and cons to using it, which I'm not going to discuss on this actual video. But just know that I did use it for that. Know that the no stack protector option for GCC does nothing to prevent heap corruption and buffer overflows on heap memory, which is to say that this code down here, which you can try on your own, will corrupt the heap, even if you have stack protector turned on, it's not going to matter. And that's it. Hopefully everyone is smart having watched this video. If I forgot to cover something or you'd like to request a video, post a comment below. And if you enjoyed this video, smash that like button. And don't forget to subscribe so you don't miss new videos. See you next time.